On April 22, 2026, a malicious payload lived inside an official software distribution channel for exactly 93 minutes. During that brief window, developers who downloaded version 2026.4.0 of the official Bitwarden CLI received a poisoned package. No Bitwarden employee was tricked into clicking a link. This attack happened without phishing campaigns, without social engineering, or standard endpoint compromises. The threat actors achieved a direct, unhindered intrusion into Bitwarden's own CI/CD pipeline infrastructure. Once inside, they used Bitwarden's legitimate NPM publishing mechanism to distribute their code to the public. They were not hunting for end-user passwords or vault data. They were after the elevated permissions inherent to developer workstations and build environments. Bitwarden serves over 10 million users and 50,000 businesses, creating a high-stakes environment for any supply chain compromise. Within these organizations, the Bitwarden CLI holds a privileged position, often used for secrets injection and automated deployments in CI/CD pipelines. This incident shows how a highly resourced engineering team's automated pipeline was turned against itself. Compromising a trusted developer tool is more effective than breaching individual machines, as it allows attackers to run malicious code with the existing permissions of the build pipeline. The path to distribution began at the start of the CI/CD pipeline, specifically within the GitHub Actions workflow environment. Using stolen credentials, the attackers compromised a transient branch upstream of the final build. This flowchart shows how the attackers quietly embedded their payload into a legitimate build artifact, specifically targeting a file named bw1.js. From there, the poisoned workflow migrated down the pipeline toward the NPM registry distribution phase. This brings us to trusted publishing, an OIDC-based, tokenless publishing system widely considered to be a hardened security path. The security community designed trusted publishing specifically to eliminate the risk of long-lived token theft. The threat actors did not break or bypass this system. They relied on it to validate their work. Because the upstream workflow was successfully authenticated, the trusted mechanism cryptographically signed and published the malware on the attacker's behalf. The mechanism built to secure the supply chain acted as the primary distributor of the malware. This methodology connects directly to the broader CheckMarx campaign, sharing identical tooling and operational signatures. Both campaigns rely on a persistent tactic, tampering with build outputs immediately prior to distribution to hide their tracks. Securing the final endpoint of a software pipeline is ineffective if the upstream workflow validation has been compromised. Downstream, in the local developer environment, the package arrives. The bw1.js payload executes quietly in the background the moment a developer runs npm install. It immediately harvests high-value targets, GitHub and npm tokens, and local SSH keys. It then sweeps for secondary targets, collecting local.env variables, terminal shell history, and stored cloud credentials. To secure the stolen data prior to exfiltration, the attackers used the AES 256 GCM encryption standard. The exfiltrated data is sent to a malicious server hosted at audit.checkmarx.cx, which mimics a legitimate security domain to avoid detection. Typo squatting a security company's domain allows outbound malware traffic to hide inside standard audit logs. After the initial data theft, the payload transitions into an active weaponization phase. If the malware discovers active GitHub tokens on the machine, it begins to use them. The payload uses the stolen token to recursively inject malicious actions workflows into adjacent repositories the developer has access to. This lateral movement expands the breach from a single machine to the wider organization. This persistent access reaches every CI/CD pipeline the compromised developer's token has permissions to touch. The payload automates the replication of its own attack vector, turning a stolen token into a new distribution point. Researchers noted that the malware contained ideological branding and manifestos referencing Shai Hulud and the Butler Jihad, pointing to a campaign evolution or a splinter group. A single infected endpoint acts as a self-replicating launchpad, turning an internal breach into a persistent source of poisoned code. The Bitwarden compromise is not an isolated incident. It is part of a systematic pattern. This exploit connects directly to a campaign that has targeted other developer tools, like Trivy and LiteLLM, since early 2026. These threat actors are now moving toward a new attack surface, Model Context Protocol, or MCP servers. This diagram reveals the shared infrastructure between these attacks. The bw1.js payload and a previously analyzed MCP payload, MCP addon.js, communicate with the same command and control server. As MCP servers proliferate across AI-assisted developer toolchains, they are becoming high-value targets for supply chain actors. Any environment that installed Bitwarden CLI version 2026.4.0 during the April 22nd window must be treated as compromised. Affected users must immediately rotate all local secrets, SSH keys, and cloud provider credentials. Network administrators should hunt for outbound connections routing to the typo-squatted checkmarx domain. DevSecOps teams should audit their GitHub Actions for any unapproved workflows created on transient branches. To restore a secure environment, developers should downgrade the Bitwarden CLI to version 2026.30 or use official signed binaries. Bitwarden confirmed that end-user vault data was untouched, as the attackers focused specifically on the developer pipeline. The critical vulnerability in modern software architecture is no longer just the application code, but the integrity of the build systems used to ship it.